Hi, I'm Thomas Wang and I am presenting our work, Multimodal Transfer Learning for Grasping Transparent and Specular Objects. There are many methods today that perform depth-based grasping and achieve strong performance. In this video, you can see a depth-based grasping method grasping normal, opaque objects. These methods work by using depth sensors to estimate the object shape, and then reasoning about the shape to determine a good grasp. In this video, you can see opaque object geometry estimated with a depth sensor. But depth sensors have difficulty estimating the shape of objects that are transparent or specular. The video shows the geometry estimated for such objects. Commercial depth sensors use infrared light to estimate geometry, which fails on transparent objects because the infrared light passes through the object. The resulting depth image is mostly the flat surface of the table. For specular objects, the structured light scatters and does not return to the object, leaving holes in the geometry. Because of the difficulties with depth sensing for transparent and reflective objects, depth-based grasping fails on these types of objects. Previous work on grasping using RGB images have demonstrated the ability to grasp transparent objects. However, these methods either require many real-world grasp attempts, multiple viewpoints per test grasp, or human annotations. Our method just uses a single RGBD image at test time and does not require any real-world grasp attempts or human annotations. Other methods for dealing with transparency and specularity for grasping require either specialized hardware in the form of a light field camera or training with high-fidelity simulations of transparent objects with the hope that the simulator has enough fidelity or diversity to transfer to the real world. In summary, unlike previous work, our work requires just a single image recorded from an RGBD sensor. We do not require real-world grasp attempts, human annotations, specialized hardware for training, nor simulations of transparent or reflective objects. We leverage a pre-existing depth network for transfer learning. In our case, the pre-existing depth network was trained on a simulator for depth-based grasping of opaque objects. However, our method does not require simulating transparent or reflective objects. In the image below, we show 3 rows of objects: opaque, transparent, and specular. The opaque objects in the first row have well-estimated geometry from the depth sensor, as shown in the depth image on the right. However, the transparent and specular objects, shown in the second and third rows, fail to appear or are missing parts of their geometry. On the other hand, these transparent and specular objects are more clearly visible in the RGB images, shown on the left. Our method leverages this RGB data to learn to grasp transparent and specular objects. We focus on planar 4DOF grasps of transparent and reflective objects, and we leave for future work to extend our approach to 6DOF grasps. We collect a dataset of paired RGB and depth images of opaque objects. We capture these images in our environment with the depth sensor we plan to use for grasping. Because this data does not require any real-world grasps, it is fast and easy for each user to collect data of this type in their own environment. The images shown here are some of the images of our dataset. In total, we use 250 such images. Our method requires only this dataset of paired RGBD images, as well as a depth-based grasping method that can grasp opaque objects. In our case, we use previous work for depth-based grasping of opaque objects that was trained in a depth-only simulation using grasp quality metrics. We train the RGB network using only opaque objects. Our method works as follows. We first take the depth image of an opaque object and pass the image through a pre-trained depth-based grasping network. Because this is an opaque object, the depth network outputs reasonable predictions about how this object should be grasped. We then use this prediction to supervise the training for the RGB network. The RGB network is trained to imitate the output of the depth network for these opaque objects. As a reminder, this method only requires paired images. We do not require any real grasps. At test time, we capture a paired RGBD image of an object. This object might be transparent, as shown here, or it might be reflective or opaque. We input the depth and RGB images of this object through each network and average the result to obtain our grasp success output. We considered a more complex way to combine the network outputs, but we found that averaging the results seemed to work pretty well. So why does our method work? The depth-based grasping network outputs a reasonable grasp prediction for opaque objects used for training. The RGB grasping network learns to grasp objects by imitating the depth network on opaque objects. The RGB grasping network generalizes this training to transparent and reflective objects, which appear similar to opaque objects for an RGB network, even though these objects look very different to the depth network. Combining the output of both networks may help our method be more robust to changes in visual texture like lighting variations. We evaluated our method on grasping both isolated objects and objects in clutter. We evaluated our method on sets of opaque, transparent, and specular objects with 15 objects in each set as shown here. These objects are separate from the ones used for training. The task is to pick up objects in the workspace and place them into a bin. We first demonstrate that our method is able to grasp opaque objects with similar performance as the original depth network. In the top left corner, you can see the view from the depth sensor. Our method is able to consistently grasp opaque objects, obtaining similar performance to the depth-only grasping method. Furthermore, our method is also able to grasp transparent and specular objects. Please see the video submission for the full clips. On grasping isolated objects, our method achieves similar performance on grasping opaque objects. However, our method significantly outperforms the depth-based grasping network for grasping transparent and specular objects. Similar results are observed for grasping objects in clutter as well. To evaluate the robustness of our method, we conduct experiments in which we vary the lighting of the environment. To create extreme lighting variations, we turned off the overhead lights and used lighting from a lamp placed to the side of the objects. Our method still obtains reasonable grasping performance even under such extreme conditions. Quantitatively, our method does not perform as well as under normal lighting conditions. Still, our method performs similarly or slightly better than the depth-only method for transparent and reflective objects, even under such extreme lighting conditions. We note that such extreme lighting situations are unlikely to occur in most operating environments. Here is an example of a failure case under extreme lighting conditions in which our method mistakes a shadow for an edge of an object. Here are 3 common failure cases for our method. On the top left, our method sometimes misdetects transparent regions of an object, particularly in clutter. On the top right, because we are only using pinch grasps, certain objects can roll or slide out of the gripper. On the bottom, our method fails to consider object mass distribution during grasping. In conclusion, we train an RGB grasping network to imitate a depth-based grasping network on opaque objects. We then combine the 2 networks to grasp opaque, transparent, and reflective objects. We'd like to thank our sponsors for funding this research. Thank you for watching, and please see our paper for full details.